Hello, so today we're going to solve problem 221, maximal square. For my subscribers who watch my videos every day, this is an essential moment in this video series because I have officially finished all of the graph problems and we're going to move towards some more interesting and more apparent and let's just say more common problem types that you'd see in an actual interview, and that is dynamic programming. So probably for the next couple of months, I'm going to be doing exclusively dynamic programming problems because I'm going to try to get through at least one every single day. Of course, dynamic programming is a core concept of data structures and algorithms, and then I'd anticipate that if you're watching this video, you have at least some knowledge of how dynamic programming works. Just to summarize it quickly, the idea is you build information based off information you've already found. So you don't want to reinvent the wheel. You don't want to recompute something you've already computed. Try to save information you've already computed and use that to compute subsequent information. And that way you can get an efficient way to solve a problem. Okay, so with that said, let's get right into this problem. So 221 maximal square. So you're given an m by n binary matrix filled with zeros and ones. Find the largest square containing only ones and return its area. Okay. So it has to be a square, right? So this answer would be 4, right? Because you have an area of 4. So 1, 2, 3, 4, or 1, 2, 3, 4. Right? It's not the rectangular space. So it's not this 6, this 3 by 2 rectangle. It has to be completely square. And then you just return the area of that square, right? So for this problem, there's only 2 single one area squares. So you return 1. This problem, there's one area 1 square. This problem, there's no area square. So I think the simplest way to solve this without dynamic programming would be to look for each square size, right? Each possible square size. So for this problem, there's a square size of 1. You could have a square size of 2. You could have a square size of 3, and you could have a square size of 4, right? Size meaning the width and the length, right? A square couldn't get bigger, right? You couldn't have a square of length 6, right? Because that would overcome the actual space of the grid. So you could and we're not going to do this, but I'm just saying you could mention this in an interview, especially if you don't know where you're going, just to buy a little bit of time. If you have sufficient time, just kind of say okay, I could look at every single possible square and see if it exists, right? So I could look at each 2 square. So let's go ahead and get this grid. So I conveniently already drew the grid here. Don't mind this. This is me. All right, so here's the grid here, right? So what I'm saying is you could look at each square of each possible size, right? Like this. So you could look at this square, then this square, and this square, and this square, so on and so forth. And then you could look for each square of length 2, right? And you could check that. So you could look at this grid and see if every single cell within this potential square is 1, and then this one, and then this one, and here, then here, then here, then here, then here, then here, right? And you could check if those squares exist. And then you could check a 3 by 3 square, right? Just so we make this point totally clear. Right, now we could check this as well. So we could look at each 3 squares and say, okay, is everything inside this blue 1? No. Here, no. Here, no. Here, no. No, no. And so on and so forth. Now, obviously, that's going to be really inefficient, right? Because how many squares do you have? Well, that's the min of m minus the min of m and n, right? You have min of m and n squares that you could possibly have, and for each square, you'd have to traverse every possible location of that square within the grid. So you're gonna have the min of m by n, and then for each one, you have to do the max of m by n operations. So And then for each square, you need to look for a number of elements inside of it, and that's m by m, right? So we're talking like m squared, m cubed, n cubed if n is greater than all three, right? So we're talking about a cubed algorithm here, not efficient. Now there's a linear time algorithm, and that is the following, okay? So how do we apply dynamic programming to this? Well, let's look at this system and let's actually adjust this so that we have a 3 square. And the reason why I want to do that is just because it's a better example. So let's say that this was the grid that was given. And just by eyeballing it, right, you can tell that the biggest square is this 3 by 3 square here. Okay. So how would you use dynamic programming to find this square efficiently? Well, we can think of any square as having an edge that you can check, meaning that I guess the key observation is, right, for this square, if we could look at this grid cell, and we've already looked at all these previous cells, can we just look at one cell and use information that we've gotten from looking at all the cells that are highlighted red and determine if a square exists here, right? Well, let's see. So if we look at just this cell, there's just a 1 by 1 square. All these cells at most can have a 1 by 1 square because they're on the edge, right? So it can never look to the left, right? Because I'm trying to build out squares. Let's imagine I'm trying to build out squares where I'm figuring out the size of the square by looking at the bottom right component of the square, right? Like I can figure out this is a square here. Sorry, this is a square here by looking at this bottom right component. And how would I do that? Well, one way you can look at a square to say, let's say I had an n by n square here. Okay, so this has n dimension here and n dimension here. And I'm looking at this last element here. What would it take for this entire thing to be a square? Well, if this component here was a square, and this would be an n minus 1 by n minus 1. I don't know why I did it like that. An n minus 1 by n minus 1, right? If that was also a square, right? And since we're always looking at the bottom corners, if this last cell in the grid had information about the square, right, that it was an n minus 1 square, well, that would work if these were all 1s up to x and these were all 1s up to x, right? So if I'm looking at any element here, right? So if I'm looking at this element here, if this previous element has a square of some size, and these are all 1, and these are all 1, then you have a square here, right? So what you can do is, in the bottom right corner of a square, you can save the size of the square the largest square that exists at that cell. And then for any subsequent system, you can run this process here and say, well, if my up to the left, right, to the left 1 and up 1, if there's a square in this cell and they're all 1s here or they're all 1s here, there's a square in this cell, there's all 1s here and there's all 1s here, then there's a square of some size in this subsequent cell. Okay, so let's go ahead and run through that quickly. Okay, so again, for all of these cells, they only have size 1, right? So this just has size 1 and 1, right? Because this is the bottom right of the square. So we look at all of these, we get nothing. This, nothing, because there's nothing to the left. Well, what happens here? Well, to the up and to the left, there's a square of size 1. I have all 1s to my left, and I have all 1s above me. So this is actually, in this cell, there's a square 2. Right, there's a 2 by 2 square, and maybe we'll draw it in red. And then likewise in this square, we can say, okay, well, there's all 1s to my left, all 1s above. So I also have a 2 by 2 square here. Now, how would you stop it from saying, well, how do you not have a 3 by 3 square? Well, for this system here, right, it has 3 to the left, right, and it has 2 above. So that's 3 from the left and 2 above, and then there's a 1 by 1 square in this top position. But since the thing has to be a square, right, I can't have a square has to have the same shape, and it's going to be constrained by the minimum shape from here and here, right? If I have 3 to the left and 2 above, the biggest square I can make is a 2 by 2 square, right? Because I'm constrained by this system. It has to be a 2 by 2 because I don't have a third system here to fill out. So really the square in this position has to be the min of whatever's to my left, the number of 1s I have going left, the min of that, and the number of 1s I have above me, and the largest square in my upper left position plus 1. Right, so what's a good example of that? Let's imagine that here, let's imagine that here, this was a 1. And then let's do this. So when this system is done in this position, it's going to find this 3 by 3 square here, right? So then it's going to update this grid value to be 3. So then once you get here, you're going to say, okay, well, I have 2 above me. So this is 2. I have 1 to my left. And then, oh, what square do I have in this position? Oh, I have 3. So I have a larger square in this position here. But I'm still constrained by the widest and the highest, right? I'm constrained from my left and above. Because the largest square I can make in this space is here. So if all these positions were D, right? The D at IJ is what? Well, it's going to be the min, right? Because I'm constrained by the smallest thing I can make, right? Because if these were all 1s, yeah, we won't do that. But you get the point. I don't want to keep making things too complicated. It's the minimum of what? Well, whatever square I have to above me and to the left, the number of 1s to the left of me, and the number of 1s above me, or up, we'll call it above, I guess, to the left of me and above me, right? So that's the square that I can put here, right? For some cell here, which is IJ, these no longer are the case. I have the number of 1s to the left of me at left IJ, and I have the number of 1s that are above me, which is above IJ, and then I have the square that's in this position, which is D I minus 1, j minus 1. Right, so this is the formulation to find the square. And if we process things like in this order, you'll notice that any cell I stop at, I have information about things, the square above me. I'll have information about what's above me and information to what's the left of me, right? If I stop at any place, that's the case. Here, right, I always have information about stuff to my left, above, and the square that's to my upper left. Right, so there's actually a one-time pass way to do this. I can literally find all the information about the number of sequencing ones, right? I could fill up this left array, I could fill up this above array, and find values for D. So we won't do the one-pass solution because it makes the code really ugly, but I'll kind of show you the basic idea about how this is supposed to work. So what we'll do first is we'll populate the, well, actually, the first thing I'm going to do is, you'll notice how matrix has ones and zeros as like letters instead of numbers, right? They're characters and strings. So first thing we're going to do is we're going to fix that. Right, so let's look at each I in range length of matrix. So this, you don't need to do this, but again, I'm not focusing on having the fastest solution, only the fastest worst case runtime solution. So I'm going to have a solution that's in the same realm, right? It's going to be still same time complexity, but it would take a little bit longer because I'm doing some operations additional times when there's more convoluted ways that you can cut out some of the extra operations that I'm doing. But it doesn't affect the runtime in terms of time complexity. So I'm just going to do that for the case of making this problem a little bit easier to digest. Okay. So I'm just going to set it to the int version of itself. Okay, because I don't want to deal with these letters anymore. I don't know why this problem's even given where there's strings. It's kind of silly. So we have this idea of what's the left of me, right? And we'll go through that really quickly. And then we'll have the same thing for above. Okay. So let's look at this graph here. And how would we create this left array? You know, what's to the left of me? Well, you could just 1, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5. Make me a square. That's not even nearly the square I wanted to draw. Because I did 1, 2, 3, 4, 5. Whatever. Okay. Okay, so we have 1. So when we look at this system, we can say we've seen 1 in a row, 0, 1, 0, 0, 1, 0, 1, 2, 3, 1, 2, 3, 4, 5, 1, 0, 0, 1, 0. So what did I just do? Well, I'm trying to find a running sum of the number of ones that I've seen to my left. So when I look here, I say, how many ones have I seen to my left? 0. I'm a 1, so I set this to 1. How many ones have I seen to my left? 1. But since I'm a 0, that cuts off the number of ones I've seen in a row. Same here, same here, same here, same here, same here. Okay, here, I see a 1. I have 0 ones to my left, so I'm a 1. Here, I see a 1 in the cell, and I have 1, 1 to my left, so I increment it to 2. Here, I see a 1 in the cell, and I see 2 1s to my left, so I increment this to 3. Here, same situation, right? I see a 1 in the cell and 0 to my left, so I set it to 1. Here, I see a 1 in the cell, and I see a 1 to the left, so I increment this to 2, so on and so forth. And then you can do the same thing for columns, right? You could start here and say, I see a 1 in my cell and 0 above, so I set this to 1. Here, I see a 1 in the cell, and I see 1 above, so I set this to 2, yada, 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 right? Here, 1, 2, 3. Here, I see a 0 in the cell, so I have to set it to 0, right? Because when you see a 0, it cuts off the fact that you see a running sum. And that way, you can calculate things to the left of a cell and things to the right of a cell, right? Because that was the idea of this here, right? Because we wanted stuff that was to the left. and we want the stuff that was above. It's getting really sloppy here. So let's go ahead and, so this would be to the left, right? That's what this cell would be. So let's see if we can figure that out quickly. Well, every time, that's Sunny in Philadelphia reference, by the way. We'll say to the left is 0, because every time you start a new row, it zeroes out, right? Because there's nothing to the left of this cell ever. So it's 0. Now, if the matrix at ij then left will plus equal 1. Or you don't even need to do that. You don't even need this left idea. You could just say, So I'm trying to think of the nicest way of doing this. So if matrix ij equals 0, then you have to set left of ij to 0, right? Because if something equals 0, you can't even consider the things to the left of you. Otherwise, you say, well, left of ij will plus equal left of I minus, or no, left of ij minus 1. Right? So the cell to my left, just add equal its running sum into my running sum, which will just plus 1 to whatever value I have. And then, I think you can also, then you could do the same thing for above, right? Above ij. So you could do these in one swing. So maybe this is easier to do the one pass solution. Aij equals 0 as well, right? Because if my cell is 0, it doesn't matter what's above me. I can't consider it because my cell 0, it cancels that running sum. So left of ij equals left of ij plus left of ij minus 1. And then a of ij equals a of ij plus a of I minus 1j. So now you have the formulation for what's above you and what's below you. And then you could say matrix at ij. So now we're doing the computation. It's the min of what? Well, if you have a matrix in the top left, right? So that would be a row above. So a row above and then to the left 1. If that's a matrix, you could plus 1 to it, right? Because when this system is a square and you have enough space in both sides, then you can create a square that's 1 greater. And then whatever's to the left of me and whatever's above me. And you can only do that calculation, well, so what I don't want is to set this to 0 if the value is actually 1. So we'll only, okay, well you can include itself, right? Because if there's 0 to the left and there's 0 above, but you set this to 1, so this would then be 1. And if that was 0, it would be 1. No, so it's fine. You don't need to do all that. And at the end, you just return the max of a row for each row in matrix. So if we print out, so let's just look at the row in left. Let's print R. So you can see that we get this corresponding Why'd I call it R? Oh, yeah. So these are all 0, so that's not good. Right, this gets not, because this is 1 for the matrix. Okay. So I changed it to a different test case. I'm an idiot. Okay, so let's look at this test case. Let's see how it works. So let's compare that to what we did here. So 1 0 1 0 0 1 0 1 2 3 1 2 3 4 5 1 0 0 1. Okay, that looks good to me. And then let's do the same thing for above. Right, we didn't write the code for. I mean, we didn't walk through the case. But this has 1 2 3 4, which is expected, right? 1 2 3 4 0 0 1 0 1 2 3 0 1 2 3 0 1 2 0. Okay, so that works. And then why is this failing? Well, if we look at matrix at the end, right? So let's do that too. Because remember, matrix now is going to have the value. Each value will be the largest square where that's the bottom right of the square, right? Print R. So if we look at this matrix, right? Let's print out the cells given this condition here. What does it tell us? We have 1, 1, 1, 1. Right. I'm just gonna type out. Why did that close? Just gonna type out the square that I see here. Right. So I have a 1 1 1 1 0 0 1 1. So 0 0 1 1. Just so you see exactly what this matrix is giving us in terms of the information it's providing. 0 1 2 1 0 1 2 0. So what does this give you in terms of information? Well, there's a 1 square here, 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 1 square here, 1 square here, 1 square here. This is a 0. I was like, that doesn't make sense. That'd be a 2 square. A 1 square here, right? A 1 square here, a 1 square here, a 1 square here. And then there's a 2 square that the bottom right is here. There's a 2 square here, which is what we expected, right? Given this, like, there's a 2 square here, 2 square here. This system's telling us the same thing. But this is telling us there's a square with length 2 and height 2. Now, if you've taken geometry or whatever, you know, that's the length of the square, but we want to return the area of the square because that's the number of ones within the square. So to find the area of a square, you just take the side length and square it. Right, so all we have to do is take that max and then square it at the end, and we should get the right answer. Okay. Now, just for the sake of this problem, we're going to go ahead and let's just go ahead and do a one-pass solution, just so we can say that, yeah, we've done a one-pass solution for this problem. So you could technically problem is that this is one. That's why it's so annoying to do it like this, because there's always these like edge cases you have to think about when these are letters and not numbers. So if this is, you could just do it at each cell. You could just say, I'm tired of playing this game. So each time you do an operation, you just convert it to an integer. Then you don't have to think about it. So now it's one pass. This is going to affect our runtime too, because we shouldn't be just printing stuff out. Okay, but now it's playing this weird game. Why? See, this is why it's so annoying. I set it. Don't convert it. It's just, why did they provide a problem like this? It's just so annoying that they did that. If it equals 0, okay. Just force convert it to int here in case it isn't an int. And then map it to an int here. Ugh. The things we do for a one-pass solution, it's just ridiculous. All right, there's your one-pass solution. Let's see if it's any faster. Doing a lot of conversions now, and I'm probably over-converting. Yeah, I'm not going to worry about the fact that it's no longer a one-pass solution. It's fine the way that it is. All right, guys, see what happens when you try to make it one pass out. Everything looking good. So what's the runtime of this? Well, in order for this to work, we're going to look at, well, you can just look at this loop here, right? We're going to have to look at each element. So it's an n by m grid. So that means that there's nm elements. So it's n by m. All right, this is an m by m problem. So runtime O of n by m. We have to create n by m space for L, n by m space for A. So n times m space, n times n time. So just to write that down. So time complexity is O of mm. Space complexity is big O of nm. All right, there you go. I apologize if this video was kind of clunky. This is one of the first dynamic programming problems that I've tried to address on this channel. So I'm not as strong at explaining this as I am graph problems, but I think as I kind of continue to do these problems, I'll get better. All right, guys.